Good day! In this video, we will be discussing all about fabric filters. Here are the topics covered for this presentation. A fabric filter is an air pollution control device that removes particulate matter from a processed gas stream before it is emitted into the atmosphere. Dust-laden gases come in contact with filter bags inside the baghouse. Depending on the type of fabric filter, dust comes in contact with the filter bag and either collects on the inside or the outside of the bag. Let us tackle some terminologies that will be used in this presentation. Baghouse is a common term for the collection device that uses fabric bags to filter particulate out of a gas stream. The filter bags are mounted on a tube sheet and enclosed in a sheet metal housing. Frequently, the term fabric filtration is used, partly to be technically accurate and partly to distinguish the technology from water filtration. Finally, a fabric filter baghouse system includes the bag cleaning system, dust collection hoppers, and dust removal system, so the total system involves more than just filtration. It must be understood that the mechanism that achieves filtration of small particles from a gas stream is not simply sieving. Here are actual pictures of fabric filters or baghouse. The one on the right is a modular baghouse dust collector. The principle of fabric filter operation is filtration, which is efficient, reliable, and economic. In a fabric filter, flue gas passes through a felted or woven fabric, and then the particulate matter is collected on the fabric. In a fabric filter, the flue gas entering the inlet nozzle strikes a baffle plate, which causes larger particles to fall into hoppers due to gravity. The flue gas then flows upward into the tubes and outward through the fabric, leaving a layer of particulate matter on the bags as a dust cake. In order to further understand how a fabric filter works, here is a short video. There are many different sizes and designs, but baghouses all operate in the same basic way. 1. The dust-laden or particle-laden air or gas stream enters the baghouse and travels along the surface of multiple fabric tubes and then passes outward or inward through the fabric. 2. The larger particles fall down into a hopper while the smaller particles accumulate on the fabric surfaces. 3. A cleaning mechanism occasionally removes the particles from the fabric tubes and they fall down into a hopper from which they are discharged. And lastly, the clean air or gas stream exits from the top of the baghouse. Moving forward to the baghouse size, the air-to-cloth ratio is simply the gas flow rate divided by the fabric collection area. Volume per unit time divided by area reduces to units of length per unit time, so the air-to-cloth ratio is also called the superficial velocity. Typical air-to-cloth ratios for shaker and reverse air baghouses are 2 to 2.5 cubic feet per minute per feet squared. Typical ratios for pulse jet baghouses range from 3 to 10 cubic feet per minute per feet squared, with recent design practice being close to 4 cubic feet per minute per feet squared and lower. A high air-to-cloth ratio requires a smaller baghouse which is less expensive. If the air-to-cloth ratio is too high, the baghouse may experience difficulty in maintaining the desired pressure drop despite frequent cleaning. A low air-to-cloth ratio, on the other hand, provides a large collection area, so dust cake buildup and pressure drop increase at a lower rate than a high air-to-cloth ratio. A baghouse removes particulates or gas release from commercial processes out of the air. Fabric filters are one fairly simple method that can be used to remove dust from the flue gas. In some gases, they can also remove acidic gases if they utilize basic compounds. Here are some of the pollutants removed by using fabric filter. First, we have oxides of nitrogen such as nitrogen dioxide, sulfur oxide, and the most common one is sulfur dioxide, which is a colorless gas with a burnt match type smell. We also have particulate matter and other gas pollutants. Today, fabric filter technology is often prescribed as a part of a solution for a plant processes that not only has particulate matter in its process, but also includes oxides of nitrogen, sulfur oxides, mercury, and some other form of gas pollutants. Moving forward with the advantages and disadvantages, let's start first with the advantages of a fabric filter. First is high removal yield for coarse and fine dust. Varying load does not influence pressure drop and efficiency. Collected dust can possibly be reused in the process. Residual emissions are determined by incoming concentrations. It is relatively easy to use. And lastly, reduced sensitivity to particle size distribution. Moving forward with the disadvantages, maximum operating temperature is limited to 550°F unless special fabrics are used. Fabric bags tend to burn or melt readily at temperature extremes. It has also high maintenance and fabric replacement costs, and bag houses are difficult to maintain because of the difficulty in finding and replacing even a single leaking bag. Also, as a general rule, about 1/4 of the bags will need replacement every year. Lastly, we have problems in handling dust which may abrade, corrode, or blind the cloth. Moving forward with fabric properties, key performance properties for fabric filtration media selection include maximum allowable temperature, chemical resistance, abrasion resistance, weave, weight, and strength. Some of these properties are listed in Table 23.1. Temperature is a key flue gas property that deserves first consideration in bag material selection. The choice of fabrics that withstand temperatures about 400°F is limited and high-temperature fabrics are expensive. Once the material is chosen, the next key selection parameters are the weave and the weight. Woven fabric threads includes the warp, which is the thread that runs lengthwise in woven goods, and the fill, which is the thread that interlaces the warp. Next, we have felted fabrics, and they have woven-based scream to give structure to the cloth, with the scream filled in with random needle punch fibers. The felting process is economical because the felting machine can be run at high speed. Felted fabrics also may be thicker than woven fabrics for the same weight, so more time is available for diffusion to be an effective cleaning mechanism. Therefore, new felted fabric can produce higher particulate removal efficiency than new woven fabrics. Typically, shaker and reverse air bag houses employ woven fabrics. Pulse jet bag house employs both woven and felted fabrics. Let us now discuss the three types of fabric filters. First, we have shaker bag houses. The oldest cleaning mechanism is to stop the gas flow through the fabric bags and shake the bags to knock off the dust cake. Generally, the dirty air enters the bag house from the bottom and is pulled through the inside of the bags where the dust is collected. The cleaning process is mechanically shaking the bags, and the cleaning process is offline, meaning that the system must be shut off for the shaker to remove the dust. Here are the following specifications for the shaker bag houses. Duration is 30 seconds to few minutes, frequency of several times per second, amplitude of a fraction of an inch to a few inches, an acceleration of 1 to 10 g, and typically the motion is imparted by an electric motor. Next, we have reverse air bag houses. Reverse air bag houses or fabric filter collectors are similar to shaker collectors. Reverse air cleaning involves gently blowing clean gas backwards through the fabric bag to dislodge the dust cake. Gas flows enters the bag from the bottom and dust collects on the inside of the bag. To clean, a portion of the clean gas is withdrawn from the clean side manifold using a fan. The reverse air valve opens and low-pressure clean gas is gently blown backwards through the fabric. The reverse air fan develops a head of only a few inches of water pressure. A primary advantage of reverse air cleaning is that very large bags can be used. The bags can be 12 or more inches in diameter and 30 to 40 feet long. Another advantage of reverse air cleaning is the potential of increased bag life from the gentle cleaning action. Moving forward, we have pulse jet, and we will first discuss the high-pressure pulse jet. A vigorous and very common cleaning mechanism is high-pressure pulse jet. It uses a very short blast of compressed air, about 70 to 100 psi, to deform the bag and dislodge the dust cake. A schematic of a pulse jet bag house is shown in Figure 23.4. The process is such that as the dirty air enters the fabric filter, the dust or particulate matter is collected on the outside of the bags as the air passes from the outside to the inside, building up a dust cake. The clean air then exits the fabric filter. Pulsing or short bursts of compressed air cleans the bags of the dust buildup at regular intervals. Pulse jet cleaning can be done online or offline. The advantage to online cleaning is that the gas flow is not interrupted, and one of the disadvantages is excessive bag wear. Let us now proceed to low-pressure pulse jet. The bags are distended during cleaning, which dislodges the dust cake, but the pulse of air is no longer and less vigorous than a high-pressure pulse. The air supply is around 40 psi. Let us now proceed to sonic horns, or also called acoustic horns. They are sometimes used to create low frequency around 150 to 200 Hz sound wave-induced vibrations to promote cleaning. They are powered by compressed air and generate about an average of 120 to 140 decibels in a compartment. Fabric filters are widely used in various industry productions such as removal of dust from transport companies, for example in cement industry. Also processing of ferrous and non-metallic materials in foundry. In biomass burning, it helps remove the dust from the kettle settings. And lastly, it is used as a filter product for mills in coal industry. Stated in this slide are typical industrial application for each type of bag houses. Next, we have modification, and we will first tackle the modification of a coal boiler, as due to the installation of a bag filter as an exhaust for a coal boiler in Hokkaido refinery, the filter corroded in a cloth during the operation. As countermeasures, a method to replace the cloth in material with acid-resistant material, prevent acid mist from growing, adjust the unbalance in gas flow rate with the inlet being provided with a guide vane and level flow velocities in front of the cloth with modifying the interior of filter was adopted. Next, we have a new filter system combining a fabric filter and electrostatic precipitator for effective pollution control behind cement kilns. The unique configuration promotes a synergy between these two technologies, which is the fabric filter and ESP, whereby the filter bags are able to operate at a high air-to-cloth ratio and be clean without the typical concern of dust re-entrainment. Fabric filters are reported to cost between $50 to $70 per kilowatts. Reverse gas baghouses have higher capital and operating costs than pulse jet baghouses because reverse gas baghouses operate at a lower air-to-cloth ratio. Fabric filters are generally more expensive than ESPs for collection efficiencies up to 99.5%. Here we have an example of a baghouse pulse jet dust collector. It is a fabric dust collector type and has an efficiency of 99.99%. And it has a unit price of $100,000. Here are the following references used in this presentation, and that is the end of this video. Thank you very much for watching and have a great day.